Yay!
Yay! One more quick example of forces between protons, we'll keep it fundamental, is suppose these two protons are in a nucleus, like helium or anything other than hydrogen. What are the forces like between these things in the nucleus? Remember we said that the electric force is crazy strong, but obviously in a nucleus we're jamming these protons right up next to each other, so the forces must be enormous. So let's look and see what they're typically like at a nuclear distance from each other. And typically they're pressed right up against each other, whatever that means. The typical distance is R is something like 2 femtometers. That means 2 times 10 to the minus 15 meters. That's the typical separation of protons in a nucleus. So just between two of them, what's the force between them? The force is going to be K times, we said Q1, I'll just write it out, Q1, Q2 over R squared. That's the magnitude of force between them. These have the same charge, and it's the fundamental charge, so it's just going to be K E squared over R squared. So this is 9 times 10 to the 9th. E is 1.67 times 10 to the minus 27. Whoops, that's not true. 10 to the minus 19. That was the mass. 10 to the minus 19th squared. And then this distance is 2 times 10 to the minus 15th squared. All right, so let's see. This is going to be... I'm going to do... Let's just, again, roughly figure it out. I'm not interested in what the actual answer is. Let's see, on the bottom, 2 squared, that's going to be like 4. 9 divided by 4 is going to be something like, 2? 1.67 squared. 16 squared is 256, right? So that's like 2.5. So what is that? 2 times 2.5? 5. I don't know. Something like 5 times 10 to the, let's see, minus 19 squared is minus 38, and 9 is minus 29. And then on the bottom, I'm going to have minus 15 squared, so it's minus 30. Oops, 10 to the minus 30. Okay, so roughly I got something like this. And so this is going to be 5 times 10 to the 1. So something like 50 newtons. That's amazing. Or about, a newton is like 1/4 of a pound. So divide that by 4 and you get, I don't know, something like 13 pounds of force between two elementary particles. Just imagine what that if they weren't bound together, imagine what that acceleration would be. That force divided by the tiny mass of these things. That's incredible. 50 newton, a 13-pound force between elementary particles. So the forces between protons in the nucleus are immense, and in anything other than this is just helium, and like uranium has 92 protons and they're all repelling each other. So the fact that a lot of nuclei, most nuclei, don't immediately fly apart is sort of a wondrous thing. There must be, it was realized early on, there must be a stronger force, a force that's even stronger than electromagnetism that holds nuclei together so that they don't fly apart. And so this force that's a little bit stronger than the electric force is called, and we're not very imaginative, so it's called the strong force. How about that? And so that's the thing. The nuclear strong force is sort of a glue that keeps these things bound together, barely. Of course, if you get too many protons in one place, it turns out that you can overpower this because it's only a little stronger than the electric force, and then you get radioactivity, then you get unstable nuclei. Roughly. So neat. So just an example of just how strong this electric force is, and just sort of the bizarre circumstances of how there's anything at all. Why any matter, any nuclear matter actually stays together. It's sort of an amazing thing.